Hi everyone, welcome to the world of unmanned aerial vehicle. Tree mortality rates have increased steadily over time in many regions, leading to growing concern that some of forests may become net carbon sources and trigger damaging positive feedback in the carbon climate system. Massive tree mortality has already been reported in Canada. Forests in Western Canada are more vulnerable to the effects of climate change. There is already a shortage in water availability in this part of the world. It remains a challenge to properly evaluate the strength of these effects because low rates of background canopy mortality. Unmanned aerial vehicles can easily survey areas several hectares in size that encompass several hundred canopy trees. We can get high resolution data in cheaper price. Here is my study area. I carried out this study in Cypress Hills Interprovincial Park. It's located in the southern Alberta Saskatchewan border in Western Canada. Here is the landscape of Cypress Hills. The forest dominated by lodgepole pine, white spruce, trembling aspen, and occasionally balsam poplar. White spruce can be found mostly in the wet areas. Lodgepole pine are found on the ridge in the dry areas, and white spruce or trembling aspen are found in between. In this study, I show how aerial imagery from UAVs can be used to study tree mortality processes by examining how snag frequency varies with biotic and abiotic conditions across a forest landscape. There were 46 forest stands. Each stand was 250-meter by 150-meter in size. A Phantom 4 was flown, maintaining greater than 90% side and frontal overlap between images while taking RGB pictures. I used photogrammetric software Agisoft Metashape to generate 3D RGB point clouds and orthophotos. This is an example of an orthophoto. The raw point clouds were normalized to ground height by subtracting values from a digital terrain model from their heights. The normalized point clouds were subsequently used to generate 10 centimeter resolution canopy height models, which represented the height of the upper canopy surface above the ground. Here the red circles are tree canopy and the green ones are the ground. Tree tops were identified in these canopy height models by using a circular moving window 3 meter in diameter to detect local maxima. We then used a region growing algorithm to segment individual tree crowns. There were 44% commission error and 41% omission error while segmenting individual tree crowns. I used 32 structural and spectral variables for each crown segment and used these to classify the segments as live or dead and to species. Random forest model was used to classify the individual crowns. The model provided over 85% accuracy. Here the yellow color is a dead spruce and the blue one are spruce and the purple polygons are trembling aspen. We identified a total of 45,600 crown segments in our UAV survey, of which around 3,000 were classified as dead. In this figure, we can see shorter lodgepole pine trees as well as those located in stands with higher soil moisture were more likely to be dead when surrounded by tall canopy. So in the x-axis, we have neighborhood canopy height. And on the y-axis, we have probability of snag occurrence. Neighborhood canopy height is, I estimated the height of the neighboring trees located within 10 meters of an individual tree. None of the three tree species showed much change in snag frequency at different levels of soil moisture. Both lodgepole pine and trembling aspen were more likely to be dead in stands with a taller overall mean canopy height. But white spruce showed a slightly opposite trend. White spruce was also more likely to be dead in sites where it represented more than 80% of the total live canopy area. In contrast, trembling aspen were somewhat more likely to be alive in sites where they were the dominant species. So we found interspecific competition might be killing the white spruce, and maybe interspecific facilitation is helping the trembling aspen to be alive. Most of the variation in snag abundance among stands remained unexplained. The model successfully captured differences in the frequency of lodgepole pine and white spruce snags among stands, but did not have much predictive power for trembling aspen. This study was able to identify thousands of individual snags and relate their occurrence and frequency to biotic and abiotic factors. In future, in this lab, I'm gonna use UV LiDAR. UV LiDAR can provide us more information on structure and for better view of the ground. I'm also planning to use multispectral LiDAR data to classify hardwood trees because RGB point clouds were not really good at classifying the broadleaves. Unmanned aerial vehicle might not be suitable for our FMA forest inventories. However, they can be used on a smaller area to get some more detailed information. Here I would like to thank University of Regina and University of Alberta for giving me the opportunity to present this study. And I would also like to thank my postdoc and PhD supervisors. This study was done during my PhD. And thank you very much for your attention.